All right. Hello, everyone. Thanks for making it to another edition of the REYES Nuclear Physics lectures. My name is Wyatt Smith. I'll be speaking today. I'll probably give it another minute or so to let any stragglers click the link and join us. I'll be talking today a little bit about QCD, quantum chromodynamics, and some theory side stuff for strong interactions and nuclear physics. So, just a minute or so, then we'll get started, okay? All right, so I think I'll go ahead and get started. I think our numbers have come to some sort of equilibrium. And I already have my first question. Before starting, can you say if these slides will be available later? Yeah, so I will post these slides later in the same place as Vincent's slides from last week on the Dropbox. So you should be able to access it using the same link as before and see all the stuff I'll present today whenever you'd like in the future. Yeah, so let's go ahead and dive right into it. Please feel free to ask me any questions using the Q&A feature on the Zoom webinar. I'll try and pause a little bit near the end of each slide to make sure you get a chance to ask any questions you have, and I'll go back if needed. Please let me know if anything is confusing or too complicated, or if I give a poor explanation, and I'll try and fix that as soon as possible. Right. So again, I'll be talking about quantum thermodynamics, the theory of the strong force, and a little bit about hadron spectroscopy. And the goal is really to give you guys more of a flavor, a taste of how these calculations, or how theorists really approach the strong force and nuclear physics in general. So again, please ask any questions if it doesn't make sense. This isn't meant to be comprehensive or meant to teach you everything you'll ever need to know in nuclear physics, just to give you just a sense of what's up. So I just want to start by talking a little bit about, there we go, talking a little bit about the structure of modern particle physics, sort of the lay of the land, so to speak. So currently, modern particle physics is really organized into four categories, which correspond to four fundamental forces, which physicists over the centuries have sort of narrowed it down to. So these four fundamental forces basically govern all the interactions of objects and particles in the entire universe. And the four forces are, I think two of them should be pretty familiar to you guys. There's the electromagnetic force, or just electromagnetism. There is the weak force, the strong force, and then finally gravity. So I think probably gravity is the most familiar to you guys, as it's the one that you'll have some day-to-day experience dealing with. And similarly with electromagnetism, because electromagnetism, well, this is just the physics of stuff like currents and charges and stuff that makes computers work and things of that nature. But so the first and the last one, electromagnetism and gravity, are sort of more familiar. They're more like your day-to-day forces, stuff that you might think about or might interact with on a day-to-day basis. The weak force and the strong force, on the other hand, are forces which really only operate on the scale of fundamental particles, or on very, very small scales. With the idea being that, so one is a lot weaker than the other. The weak force is weaker than the strong force. I apologize for the poor naming scheme, but both of these things only matter to particles. So for the particles that we currently are aware of, they're put together in what's called the Standard Model. So frequently it's shortened to just the Standard Model, but the full name, I guess, would be the Standard Model of Elementary Particles. And this comprises basically like sets of quantum field theories which describe as much matter as we can basically understand through comparing some theory and some experiment. So what the Standard Model does is it essentially unifies 3 of the 4 fundamental forces. It unifies electromagnetism, the weak force, and the strong force, which I should note here is the force that really deals with nuclear interactions and nuclear physics. So this is the one we're going to be focusing on. Basically every known confirmed particle that exists, or every known fundamental particle that exists, is in this table right here on the right, and they're categorized in sort of by colors in this chart in sort of like 4 or 3 blocks and then 1 extra add-on. So here in purple are what are called the quarks, which I think Vincent gave a very brief description of in his last lecture. We have the up and down quarks, the charm and strange, and the top and bottom quarks. And these quarks are the things that interact via the strong force. They're the things that really, the up and down quarks in particular, really like make up nuclei and are present in the nucleus of atoms. And so these are really going to be what we're going to focus on. But I should just mention that, so the stuff in green, these are the leptons, and these are weakly interacting particles. You know, our friend the electron, probably the most familiar one out of all of these particles, is a lepton, and each of the leptons has its own corresponding neutrinos. So that's for the electron, there's an electron neutrino, and then there's muons and taus, which have corresponding muon neutrinos and tau neutrinos. So something to note is that these 3 columns on the left are typically called matter fields, and they're all fermions, meaning they're spin 1/2. And the idea is that they're organized in these columns because there's some sort of mass hierarchy going from left to right. So here, if you look at the chart, all of the masses are given in terms of these fun units, these electron volts, which I think Vincent spoke a little bit about in his previous lectures. And you'll notice that if you just look down one column, you know, all these things are relatively light compared to the stuff 1 column to the right of it. And the stuff in the middle column, the second column, is a lot lighter than the stuff that's that's one column to the right of that. So it seems like, you know, this stuff is much lighter. So, you know, living at an energy region where these things are closer, these energies are closer to energies we see on a day-to-day basis, really the up and down and electron neutrino are particles that you should really expect to see if you were just looking around you without performing any experiments, or without going to like a particle collider. So yeah, so these are really the physical particles that we care about in our day-to-day. And then on the right, on this 4th column in red here are what are called bosons. This column in red are the gauge bosons, and what they do is they mediate the three of the 4 forces on the left. So the gluon, what it does is it mediates the strong force, the photon mediates the electromagnetic force, and then the W and Z bosons mediate the weak force. And when I say mediate, what I mean is that they sort of are the force carriers. There is some sort of interaction between photons and charged particles, which sort of tell particles that they have to feel an electromagnetic force, essentially. So this photon basically tells what 2 positive charges should do when they get closer and closer together. You know, 2 positive charges should, when they get closer and closer together, exchange a photon and then realize they have to go farther apart because they're both the same charge. And that force is, again, it's sort of related. The 2 particles know about this because of the photon. And then the last particle, possibly the most famous one, you know, maybe bar the electron or the photon, the most sensationalized one certainly is this Higgs particle. And the Higgs particle, what it does is through couplings of the Higgs to the other particles, is it famously generates mass. So a lot of these numbers here, which are listed in the energies that I noted that show up in this hierarchy, these things come about because of the Higgs. The Higgs sort of tells them how much each of the particles weigh. So I mentioned previously that, so this is a list of particles, but this standard model of particles is really put together, or all these types of particles are combined into what's called a quantum field theory. And so I should spend a few moments trying to explain what I mean by that. So a quantum field theory is really a fundamental object. It's like a mathematical construct, which we say sort of exists everywhere for all time. So a field is just some function, it's some value of an object, which you pick any point in space-time, and there's going to be some corresponding value for that object. And by the word quantum, what we're saying is we're studying fields that exhibit like quantum behavior. So we have particles which manifest in the field sort of as excitations in the field, sort of like ripple on the surface of the lake. And the quantum nature of all of these particles, which sort of are excitations of the fields, can be interpreted as either like a point or a particle in keeping with quantum mechanics. So on the right here, we have some relatively simple pictures of what this might look like on sort of like a 2D plane. Really, these things, so like fields aren't just 2D, they really should exist everywhere for all time. But that's a lot harder to draw pictures for. The idea here is that so an electron right here is pictured as sort of like an excitation or like a wave packet, a little bump in the field going downwards because it has a negative charge. And then its antiparticle, a positron, is viewed as sort of like a positively charged excitation. So like an upwards excitation versus like a downwards excitation. And so electrons moving around on the surface of the field is sort of like ripples on the surface of a lake correspond to an electron moving through space or a positron moving through space. The idea is also that if you were to just consider it like on a point-to-point basis, that you would see you might be able to measure something that is higher than the average, where like the average, like sort of the sea level, so to speak, is what we call the vacuum state or the ground state. It's sort of like the energy of the field when there's no excitations, there's no particles, you have just an empty box. So I got a question, why are the bosons of type vector and scalar? I don't understand what that's supposed to mean. Okay, so this is in the previous slide. What is meant by vector and scalar refers to the spin of the particle, which so essentially the observation, one of the observations of quantum mechanics is that fundamental particles sort of behave kind of like they're spinning when you put them through a magnetic field. And a scalar particle is a particle which just has, I should get back a slide. So a scalar particle is a particle like the Higgs is a particle that doesn't have any spin. Like you send it through, you try and subject it to some force. It doesn't look like it's spinning. It doesn't have any extra quantum properties associated with spin. Whereas a vector boson is a boson which does have spin. It has spin 1 in this case. So vector equals spin 1, scalar equals spin 0, and then fermion equals spin 1/2. So I hope that cleared that up. So you'll have all these excitations in the quantum field which are spinning around and hitting each other. And the point is that in the case of electrons and positrons, when they're antiparticles of each other, they're excitations in the same field. So you might expect that when, say, a positron hits an electron, they cancel out. And so this is what people refer to, what they're talking about when they're talking about annihilations of particles and antiparticles. They're sort of oppositely signed excitations in the same fields. So it's sort of like ripples hitting each other and canceling out. So the fields are stacked on top of each other. We don't ever have just one field at a time because we essentially have a different field for every particle. So even though on the right here we have pictures of electron fields, really what we should think about it is we should think about it as sort of like a layered cake, or like a bunch of different lakes or different ponds sort of superimposed on top of each other. So there's an electron field, and there's also a photon field, and there's also an up quark field, a down quark field, a field for gluons, all the other quarks, all the neutrinos, and all the leptons, all of these things. And the idea is that you sort of have a value for each of these different fields at every point in space-time. So it's sort of like everywhere there's some number or some field value which corresponds to what's going on with that type of particle in that region of space. And particle interactions, as I just mentioned, are when different particles, different ripples sort of hit each other and do strange things, because, you know, if there's a coupling between different fields, if there's some interaction, say, between electrons and quarks, or between bosons and matter particles, then they can do interesting things. And that's sort of what we study when we do scattering experiments. So I just wanted to emphasize in the next slide that all these particles, all these ripples interfered constructively or destructively. And you know, as I mentioned, when you have like an electron and say a positron hitting each other, they can annihilate, because sort of, you know, the peak of one ripple meets the trough of the other ripple, and they all cancel out. And you know, this is sort of a nicer picture because you can see it more clearly. You can see like sort of interference between different ripples as each sort of droplet in the water propagates out. And again, this happens for in between different types of fields, because, you know, sort of when you have some overlap between the ripples, that corresponds to a particle interaction. So it can get quite complicated quite quickly, let's say. So we're not interested in just particle physics. We're interested in particularly the strong force, which means that we should really restrict ourselves now to what's called quantum chromodynamics, which is just a fancy name for the theory of the strong force, or the part of the standard model that corresponds to interactions of quarks and gluons, you know, the stuff that makes up nuclei of atoms. So the fundamental degrees of freedom of the strong force of quantum chromodynamics, which a lot of the time I'll just refer to as QCD for the initialism. So it's usually quite advantageous to think of this thing in relationship to quantum to electrodynamics, to electromagnetism. So one of the main differences between quantum chromodynamics and electrodynamics is that instead of there being just one charge, like electric charge being positive or negative, there are actually three charges, which is usually referred to as like some sort of SU3 color. The idea being that usually, you know, if you pick your colors, if you call them, say, red, green, or blue, that, you know, each of the red, green, and blue is like sort of its own version of electric charge. So there's like positive and negative, like blue or green or red, like sort of like blue and anti-blue, or green and anti-green, this sort of thing. So that's referred to as like a color charge. Like looking at what color the particle is helps us to classify particles and to think about well, what's going on in the particle physics. Another thing about QCD, about the strong force, is that it's very, very short range. The strong force at energy scales that, like the ones that we live at, typically acts on the order of 10 to the minus 15 meters. So very, very short distances, which you really only see when you're inside of the nucleus of an atom. And as its name implies, the strong force is very, very, very strong. It's about 100 times stronger than the electromagnetic force, again, at sort of an energy scale that you and I live at. And so something to note is that stuff like protons and neutrons aren't fundamental particles. You know, they don't appear in this table, but instead protons and neutrons, which make up nuclei, are typically modeled as, or are typically described as having some quark content. So here a proton is given by sort of a bound state, you know, a bunch of, or two up quarks and a down quark, all stuck together in a ball, stuck together with gluons, these little wavy lines in between. And the neutron is given by one up quark and two down quarks, again, all stuck together in like some very dense, strongly interacting ball, which you know, clusters together into nuclei when you have multiple protons and multiple neutrons all stuck together. So you get a bunch of quarks all stuck together with gluons, and that's what makes up a nuclei. So here on the right is it's a bunch of very complicated equations. This in effect is the Lagrangian, what I'm calling the Lagrangian for the strong force. So this is basically just like a one-line representation of the theory of the strong force. This is sort of like the equation that we want to solve. And I've just stuck it in for fun if you want to take a look at it. The idea is that so each of the Q's are quarks. The stuff in the middle is a bunch of complicated math. And the idea is, for each quark and antiquark term, there's some, bit of energy that corresponds to that. And then you're summing up the energies over the different flavors of quark. So the F indicates if the quark is, say, up, down, charm, strange, top, or bottom. Okay, and then the second term just corresponds to interactions of gluons, and it's given by this horrible mess down below. So that's good to know, but the idea is we want to take this theory and we want to calculate some sort of observables. We want to be able to make predictions for experiments, and we want to be able to say, okay, this is where the theory matches up with the experiment. This is where it doesn't. We should look for some explanation of that, or look for some tweaking of the theory or experiment in order to make things make sense, because we want to arrive at some understanding of the strong force. We want to arrive at some understanding of how to solve this Lagrangian. So the way one does this is typically you match theory and experiment by calculating what are called scattering amplitudes. These are the objects that Vincent spent some time to describe, and I believe his first lecture, where the idea is, imagine this picture in the middle here is inside of a particle collider. So you're accelerating some particle to very, very high energy, and then you're basically smashing in some incident particle, some incident wave into like a target, like say some other particle, like an atom or a nuclei or something of that nature. And then what one does is one sort of measures whatever comes out of it, the bits and bobs flying everywhere. And they measure what type of particle it is, how fast it's coming out. And they also measure like what angle it comes out at. So, the scattering event happens in like a detector, which is sort of surrounded in like a 360 with panels which detect particles going in every which direction. So the point is that you can measure exactly what part of the solid angle, what angular components of the outcoming particles are once you smash some particles together. And the thing that experimentalists measure is this differential cross-section, which, it's a function of some angular variables, a function of angle theta, and the azimuthal angle, which sort of like wraps around in and out of the plane the other way in 3D space from this picture. And the point is we want to match up this differential cross-section with a prediction of experiment for the scattering amplitude, which is essentially just the probability amplitude of a particle going in a direction. So I should note that, so experiment measures this thing, which is like a real number, and then we calculate the scattering amplitude, which we have to square in order to get differential cross-section. But this thing still carries meaning of probability, and the idea is we sort of calculate the probability of a certain particle flying out in a certain direction, and try and match up that distribution with the distribution of real particles that we see from experiment. And the way we try and calculate all of these scattering amplitudes is schematically through a Feynman diagram, which I'll describe presently. So here, what I've done is I've written out a very simple Lagrangian, a very simple equation that people might want to try and solve for a scattering experiment and compare theory and experiment. And so this is for, it's called phi cubed theory. This is for a spinless particle, which I'm just calling phi for now. And the idea is that each of these terms corresponds to something which, we sort of have some physical intuition for. This first term right here is 1/2, and then these are derivatives of the field of the phi particle. This thing sort of has the meaning of kinetic energy. And if you look at it, if you squint close enough, this sort of looks like a 1/2 times like a v squared, where the velocity of a particle might be like the derivative of the position of the particle. Okay, so this thing has meaning of kinetic energy, like 1 of mv squared. And then the second term has meaning of like a rest mass, from Einstein's famous E equals mc squared. This thing sort of looks like an m times something squared. So this thing has meaning of some mass energy. And then this third term, this lambda 5 cubed term, is an interaction energy. Basically, by specifying this term, I've said what types of interactions are allowed in my model for the scattering amplitude. So what we do is we sort of write this, and then we make a correspondence of solutions to this type of equation to diagrams like these down here below, in which the scattering amplitude is going to be given by the sum of contributions of a bunch of different diagrams, like this one plus this one plus this one plus, an infinitely many number of diagrams, because I can keep adding lines whenever I want, in which a line corresponds to a particle and a vertex, where lines meet, corresponds to when particles interact. So the idea here is that if I was just smashing two particles together, and if I think about time as moving from left to right, this first diagram corresponds to trying to smash two particles together, the top particle and the bottom particle, and then missing each other. So they just sort of sail on by, they don't do anything, they don't interact, nothing happens. And so a diagram like this, in which there are no like connected lines, nothing touching each other, is going to behave functionally sort of like lambda to the 0. So this lambda is the coupling constant, which you basically pick up a factor of lambda every time you have an interaction of particles. In this case, an interaction of 3 particles, because it's phi cubed. So there's sort of 3 phi's that meet together, which give you a factor of lambda. So if I were to add in some more lines and consider the next diagram over, I could say that, all right, I can think about a scattering event of 2 to 2 in which 2 particles, maybe they hit each other, or maybe the bottom particle decays into 2 other phi particles, and then one of the decay products, one of the particles, like goes up and smashes into the top particle. So this thing sort of corresponds to an interaction term like this one up here happening twice. So we'll have a factor of lambda at the top vertex, a factor of lambda at the bottom vertex. And so a diagram like this will roughly go as order lambda squared. And this sort of continues and continues on and on as you add more and more particles and more lines. If I added another vertical line in the middle here, this corresponds to a diagram which might have like a lambda to the 4th contribution, and so on. And the idea is, physicists like to use perturbation theory a lot, because it makes things easier. The point is, if you diagrammatically separate the calculation this way and calculate stuff diagram by diagram, if this coupling, if this lambda is small, specifically if it's less than 1, then you can treat everything basically as a Taylor series. What I mean by that is you can write the scattering amplitude, this function of the angular dependence, as a sum of like terms that are polynomials in lambda. And if the coupling, if lambda is less than 1, then what we can do is we can actually stop this infinite sum at a finite power of lambda and still get a pretty good result. What I mean by that is that this lambda squared term, since lambda is less than 1, lambda squared is always going to be bigger than lambda cubed. Like, if this was 1/2, for example, 1/2 squared is 1/4, and that's always going to be bigger than 1/2 cubed, which is 1/8. So every term you add adds less and less to the scattering amplitude. So if you stop at a finite number of terms, then you aren't really missing out on much. And so you can stop and say you're happy, and then, in some cases, even provide some bounds for the error you'd expect of your calculation for better matching up to experiment. So this is typically how calculations in quantum field theories are done, especially in electrodynamics and in like weak force physics. But unfortunately for us, for nuclear physicists, we don't have the luxury of doing this, and we can't really solve QCD in the same way because of a couple of reasons, which I'll describe next. So the first reason is just that it's complicated. So this first bullet point where I say QCD is non-abelian, what I mean by that is that there are hidden in the Lagrangian that I showed earlier in those complicated equations, there are a bunch of matrices which are very difficult to deal with mathematically, which make it sort of impossible to treat in the same way as I just showed. Similarly, QCD is non-perturbative. What I mean by that is that this alpha S, so this alpha S is the coupling constant for the strong force. It's sort of like the lambda in the phi cubed theory that I had on the previous slide. It's not perturbative, meaning that this alpha S is bigger than 1. So if I were to stop at, say, like an alpha S squared term, like the next term in the series, alpha cubed would actually be bigger than alpha squared. So every sequential term has a larger and larger contribution, so I can't stop at a finite number of terms. I'd have to calculate an infinite number of diagrams in order to do that. I should note that this alpha S, the coupling constant, is really a function of energy. And so this plot right here is a plot of the coupling of the strong force as a function of energy on the x-axis. And so when I say alpha S is bigger than 1, what I mean is that in the world that we live in at low energies, this thing is a lot bigger than 1, because as you get closer and closer to 0, this thing sort of asymptotically diverges and seems like it goes off to infinity, like when you go far enough to the left. And so on the x-axis here on this plot starts at 1 GeV, and we're somewhere around here, like are off to the left. And then finally, there's another issue with QCD which makes it difficult to deal with, which is confinement. And this really takes two forms. It takes a form of color confinement, meaning that you're never going to be able to really observe a single quark alone, because, well, essentially for whatever reason, there aren't any colored objects which we can observe in nature. That is, like a single quark has some definite color, it's red, green, or blue, with some amount. And the point is that of the observable spectrum of particles, we don't observe any particles with color. And so quarks, as we have learned over the last 50 or so years, only exist in bound states, which sort of neatly cancel out the color components. So here are a bunch of possible combinations of quarks which might satisfy this, where the color sort of cancels out. You could have one of each color, one of each red, green, or blue, or you could have sort of like a blue and an anti-blue, or red and anti-red, things of that nature. And this manifests explicitly in the potentials of quarks. So this final plot on the far left is a plot of the potential energy between two quarks as you try and pull them farther and farther apart. So you can think of this plot as the amount of energy it takes to separate two quarks that are in a bound state. And as you can see, this thing sort of goes off to infinity. That is, the farther apart you try and separate the quarks, it takes like an infinite amount of energy to really separate these quarks and to try and observe one on its own. So this is sort of a manifestation of this color confinement in some sense. So this is a pretty big problem. I mean, this means we can't really treat QCD in the same way that we treat electromagnetism or the weak force. So, this sort of begs the question, how do you study a theory that we can't solve? And the answer to that is by building models. So here I have a bunch of pictures of different cool pictures of different ways in which you can approach quantum chromodynamics and approach the strong force. I'll be talking about, next week, I'll be talking a little bit about scattering theory and about constraining models using scattering theory. And I believe later on in the program, there will be a lecture about lattice QCD, which is sort of about doing simulations and solving QCD numerically. But there's all these other cool approaches involving light front quantization, where you do a bunch of relativistic stuff. You can look at large n limit, meaning large numbers of colors. You can look at Hamiltonian approaches, solitons, instantons, tensor networks, Dyson-Swinger equations, all this cool stuff. So there's sort of like a big box of toys for a theorist like me to play with when we talk about like model building, and we talk about trying to find some way to solve QCD without using the old standard approaches. But by far the most effective model to date has been the quark model, which categorizes hadrons loosely into two types. And I think Vincent maybe said a word or two on this in the last lecture. So maybe you guys are already experts in all of this. But the idea that was essentially that most of the sort of standard hadrons, most of the particles which are made of quarks, that's what a hadron is, come in two types. There's either a meson, which is a quark and an antiquark stuck together, or they are baryons, where they are three quarks stuck together. So here I have some nice pictures of different configurations of mesons on the left. So here we have a bunch of different options for quarks, for building mesons using up, down, charm, and strange quarks. And then on the right, we have a bunch of baryons, which can be made using the same combinations of quarks. So the way that this structure sort of emerged, the way that experimentalists first understood the structure as being a possible explanation for all these particles which are observed in the spectrum. So all these particles, or the vertices of all these different diagrams, are particles that particles that have been observed in the spectrum. So these things were sort of pieced together slowly through studying what are called the quantum numbers of each of the particles. So each state, each particle that we look at is organized, is sort of described by using a certain set of quantum numbers. And by quantum numbers, I just mean it's some properties which correspond to like a conserved quantity in nature. So there's some symmetry that physicists understand as being important and being conserved, kind of similar to the conservation of energy, the conservation of momentum. So these quantum numbers are things that describe states nicely and don't change that much in reactions. So and another thing is that antiparticles are going to have the same quantum numbers as the particles with flipped signs, at least when we're talking about the particles in this table. So for example, if I take a look at the down quark, the first entry in this table, we can see that it has an electric charge of -1/3. It has what's called an isospin Z component of -1/2. It has no strangeness, no charm, no bottomness, and no topness. And so these numbers are sufficient to completely describe quark of the down type. So as you can see, here are all the quantum numbers for the quark, the down, up, strange, charm, bottom, and top quarks. And as you'll note, the up quark looks kind of similar to the charm quark and the top quark, in that they both have 2/3 electric charge. And the down quark, the strange quark, and the bottom quark look kind of similar. They all have -1/3 electric charge. Because as I mentioned previously, the charm and top and the strange and bottom are heavier versions of the down and up quark, respectively. But these heavier versions have some strangeness, some charm, some bottomness, and some topness, which is just a silly way of saying that like a particle, a composite particle, a meson or baryon containing a strange quark or a charm quark is in some way different because of its quark content. So there's some number associated with that difference. And as a fun challenge, if you have some time in the next week or so, what you can do if you're very bored, you can try and figure out what are all the quantum numbers for the spin zero mesons, just quark and antiquark states that you can make with just the up, down, and strange quarks. So you can take this table, combine up, down, and strange quarks and all the possible quark and antiquark combinations, and try and figure out, what states they are, what are they called, what are their properties, and if you feel so inclined. And then, so these aren't the only quantum numbers, however. These are the ones that are easy to deal with. There are a couple others that I should mention for the purpose of of describing the hadron spectrum generally. So there are also, particles can also be described in terms of JPC quantum numbers, where J is the particle angular momentum. So in this case, as I mentioned previously, particles can have some spin, but if you sort of have two particles that are stuck together in a bound state, like in a meson, like a quark and an antiquark stuck together, the point is that those two quarks can have some like angular momentum around each other. They can be rotating around each other. They can be spinning in addition to their own intrinsic spin. So here we have sort of like a spin up and a spin down. In this case, an electron, which look like they're spinning like either clockwise or counterclockwise. And then if I stuck two of these things together, they could also have an additional like orbital motion around each other. And this total angular momentum is called J. So it's this J, the subscript in the JPC. And then there's this other quantum number called P, which is the parity quantum number, which describes essentially what happens when you do a total inversion of the coordinate system. So if I were to say describe a point in space, just in 3D space, you have like an x-axis, a y-axis, and a z-axis, then I would have some point, I don't know, x, y, z. What parity does, or what the parity operator does, is it looks at what happens when you take a particle and you describe its position, not in terms of x, y, z, but then you do like a total reversal of the coordinates and you say, okay, now consider it if it was at minus x, minus y, and minus z. So the action of this inversion has some effects on the description of the state that you want to write down. And that effect is called the parity quantum number. So this thing is also very important when describing hadrons and particles in general. And then the final quantum number that I'll talk about is this charge conservation quantum number, which pops up when you're talking about what happens when you replace a particle with this antiparticle. So if I were to take like a positively charged particle, like I don't know, like an electron, or sorry, like a positron for a positively charged particle, and I were to swap it with its antiparticle, an electron, there's again going to be some change in the representation of that particle based off of switching from being positively to negatively charged, based off of switching from particle to antiparticle. And that change is characterized by this last quantum number, by the C. So it's usually written J to the P and C, where J is the spin, P is parity, C is charge conservation. And these turn out to be very, very important when describing the hadron spectrum, primarily for the reason that, even though the quark model is the best, is like the neatest explanation for the neatest explanation for a large number of particles that we see in the hadron spectrum, it very, very nicely describes stuff like the proton and the neutron. A lot of particles, newer particles that are being discovered even now, like every year at like the LHC at CERN or other particle colliders around the world, lots of these new particles are completely incompatible with description of being as a meson or a baryon, because they don't have the right combinations of spin, parity, and charge conservation quantum numbers. So here's sort of like a plot. On the y-axis is the energy, the masses of a bunch of particles, which you might expect. And on the x-axis, there's sort of just some columns here where these correspond to different JPC numbers. So these like 0++ states in this column right here are spinless particles, which basically don't change. They're both positive. They have positive parity and positive charge conservation. So there's basically no change in the description of these particles when you do a spatial inversion or when you swap with this antiparticle. So the point is that all of these green states are states that are very well described by charm and anti-charm mesons. So these are just charm, anti-charm plus excitations of charm, anti-charm, states that have some extra energy associated with them. But all of these states in different colors, this orange, purple, black, red, and blue states are all, they don't have the right quantum numbers. They don't have the right JPC. They have some other issue with them, which makes it difficult to say what the heck they are. So people say things like, okay, maybe they're like a tetraquark, maybe there's 4 quarks stuck together, maybe there's like a pentaquark, 5 quarks stuck together, like in like these. So these ones are claimed to be some sort of tetraquark, and this is claimed to be like, these blue ones are claimed to be like pentaquarks, or maybe there's something else going on. So this provides a lot of motivation for studying the hadron spectrum and for trying to build different types of models, different types of non-quark models, in order to explain what's going on. Sort of, a physicist builds a model, gets all this stuff in green, and says, all right, this looks good. And then more data comes out, and all of these orange and purple and blue and black states come out, and it's like, okay, well, now I have to sit down, refine my model, figure out what's going on, and find some alternative solutions and alternative explanations for all of this data. So puzzles like this is sort of the focus of a lot of theory today. So I think with that, I will stop the lecture portion of today. So next time I'll talk a little bit about scattering theory and about ways to constrain models based off of some functional properties of what's called the scattering matrix. But I think in the next, let's see how much time we have. We have 13 or so minutes, so I can answer any questions, or we can discuss the physics a little bit more if this is of interest to people. So yeah, thank you for listening anyways. Okay, so I see there's a raised hand from, let's see, how does this work? Vincent, are you there?
Yeah, yes, I'm there. I don't, do you see a raised hand? Oh.
Yes. So do you have a question?
Click on chat, I don't know. Can that person write? Let's see.
Yeah, you can write me a question in the Q&A.
And then if I say hi, maybe I let that person. I don't know what's happening.
Okay, so
let's clear the question that you already answered. So answer live, done.
Okay.
Answer live, done.
Okay, so I have some questions.
Okay,
first one.
Okay.
So the particle in the last slide that I mentioned, are they the particles that break CPT symmetry? So no, they don't break CPT symmetry. What they do is they defy the usual expectations of a quark model type particle. So when you talk about CPT symmetry, what you talk about is like a combination of charge and parity and T for time reversal. So the CPT symmetry is this. There's a theorem that says the combination of all these 3 things is sacred, can't be violated. But so these particles don't violate CPT symmetry. I don't think there currently is a lot of evidence for CPT symmetry. Maybe I'm wrong on that, Vincent. I'm not up to date on the specifics of
So the CPT symmetry is like a theorem saying that you cannot build, well, any theory that you build out of general principle, like, Lorentz invariance, and will have this CPT theory invariance. So in other words, with like physical reasonable assumption saying that we live in a 3+1 dimensional world, and you cannot come up with a theory that will violate CPT. So there's not such a, but of course, parity can be broken separately. CP can be broken separately, but CPT cannot be.
Yeah. I hope that answers your question. And so, okay, so there are some other questions. Could you explain parity again? Sure. Why don't I go ahead and draw a picture actually? So let's see if this works. Can you see my whiteboard thing? All right.
Yeah, we do see
Okay.
it.
So the idea behind parity is that, so if I just have like some function of x and y and z, the idea is, at every point in space, so this is just like x, y, z coordinates, x and y and z. So if I just look at a point, or let's say if I were to look at some like particle that's right here. So it's described right here as having like a certain x, y, and z component according to like where it is in this three-dimensional grid, right? This is that point x, y, and z. And if this function of x, y, and z describes a particle, then by parity, what I mean is, what happens to this function if I were to replace x and replace y and replace z with minus x and minus y and minus z, which corresponds to sort of like, what if I were to just flip all of the coordinate axes like this? So then, oh, I didn't flip all of them. One moment. So what if x went to minus x? What if y went to y? Minus y is this way. Sorry about that. Minus y is this way, and minus c is this way. But the particle, so I flip the coordinate axes, but the particle is still at the same spot, basically, right? So the question is like, how does this function change based off of flipping all these directions, based off of changing its location from minus xy, from xyz to minus xyz? So it's sort of like, what is the action of parity on f of xyz? Something like that, or something like this. And so like a positive parity state means that f of x, y, and z is equal to f of minus x minus y minus z. So it's saying like there's no change. It doesn't matter if you were to flip all the coordinates in the axes. There's no change in the function. There's no change on whatever describes your particle. Whereas a minus parity state is one that picks up a minus sign. So f of x, y, and z looks something like minus f of minus x minus y minus c. It's sort of like being odd. It's sort of like being an odd function, essentially. So I hope that makes a bit of sense. Let's see. So there is another question. The way the field is introduced is very similar to space-time. Are they interrelated? Yeah, exactly. So the point is that the fields are defined at any point in space-time. So this f of x, y, z is not really just f of x, y, z. It's like f of x, y, z, and t. Where did my annotation thing go? One second. So really, the field looks like a function of f of x, y, z, and t. So it exists in 4 dimensions. It's sort of like the fabric of space-time or something like that. Or it's like excitations in this function of 4 dimensions are particles, essentially. Okay, a few more questions. Hopefully that was sufficient. And feel free, if I didn't answer it quite enough or you have any follow-up questions, just stick them in the chat. Another question, how do theoretical physicists use mathematical models to predict the existence of new particles before they're experimentally detected? So this sort of, there's a couple of ways to do it, and it sort of is based off of your approach, right? I think most traditionally, the way a lot of new particles have been discovered has been by looking at, essentially by looking at quantum numbers and looking at different ways to couple particles to each other. So maybe I should go back to one of my slides for this one. So back when, I'm not showing my screen, hold on. Let's see. Okay, so we should be back on the presentation, I think. So back in like the first few slides, when I was talking about here, so I was talking about like Lagrangians and different terms that you add to the Lagrangian that sort of make sense intuitively and physically. So one possible way that you can predict the existence of a new particle is essentially by adding in new interactions or adding in a new field with a new particle with different interactions to the other fields. and sort of trying to write down terms that make sense based off of the properties of a possible new particle. So you would write down a theory, maybe you'd write down a Lagrangian like this, and then you would try and compare it to experiment to say, okay, yes, there is experimental evidence for this particle, or no, there isn't, based off of, contributions from these terms that would make sense if you were to stick them in, if like for a new particle. So it's sort of like people have written down predictions for all types of different particles that may or may not exist. I think most of the low-hanging fruit are probably taken at this point in terms of simple models for new particles. And then experimentalists, a big job of experimentalists is to run experiments and look for evidence of these particles to say, yes, these models work, there is a new particle there, or no, there isn't a new particle there. So I think the most recent particle we discovered was the Higgs, right? And so this was a big deal 10 or 15 years ago, essentially, when they found the Higgs, which was, people didn't know they were going to find it before they looked for it, right? Someone wrote down a model describing, how the Higgs could function and how the Higgs could give mass to other particles. And so they had to look for a scalar particle in the right mass region, and eventually they found it. So the theory was validated. Okay. A question. So
there is a request for the panelists, but I don't know how to do that. They say, would you please make a plug for people who wish to stay and listen to the next speaker? I have no idea.
Sure. Yeah, of course. I suppose Andrew Dotson will be presenting in the same webinar at noon. What is he presenting on?
Is it what Raul wrote in the chat? Is it the outreach on?
Here it is. Yeah. So Raul. Okay, so there is another talk called "Tensors and Memes: An Unorthodox Approach to Science Communication" by Andrew Dotson, and he'll be communicating his experience pursuing a PhD in physics to provide sort of representation of what it's like. So if what I've said today, if what Vincent said in the last few weeks is of interest to you, maybe you could get sort of like a peek at what it's like from the inside from Andrew Dotson, and that'll be at noon today. In 3 minutes and 2 minutes exactly. Now. So I guess I should finish up. Okay, so there's a couple questions that I'll just very briefly say about. Okay, so the first question, something that looks like electromagnetic field strength tensor in the QC Lagrangian, both in the extra index alpha, extra index A. Yeah, so it's the exact same as for the field strength tensor, except with a color index, because these things have color. So this extra superscript A corresponds to some different, basically some complicated matrix stuff, which is what I was referencing when I was talking about the non-abelian nature of the theory. But otherwise it is exactly identical, except for this extra term, this FABC, which comes in because of matrix things. Another question, is evidence for Higgs reproducible? Are the results consistent? It's reproducible if you have a huge particle collider. Yeah, I would say yes, the results are consistent. Okay, in one of the slides, you mentioned alpha S, which is what you think is the running coupling constant. Can you please explain why it depends on momentum transfer and why it's always greater than or equal to 1? It is greater than or equal to 1 in the region of low energy. In the region of high energy, you actually can use perturbation theory and get some predictions, but typically these energy regions are inaccessible to experiment, so it's difficult to still do calculations in this way. It depends on the momentum transfer. It depends on this q squared, which is the energy of the beam, because of I think the cleanest explanation is through dimensional regularization, which I probably can't describe in 0 seconds. But you should just look up dimensional regularization or check out a textbook. I might be able to send a recommendation for a textbook which has